thank you. I will present with Karan Pinto of Terra Quantum our collaboration on quantum algorithm for space. And I will start with a very short introduction of Thales positioning on quantum algorithm for space. So it is the result of a joint collaboration between Thales Alenia Space and Terra Quantum on hybrid quantum tech for space. So in Thales, we are exploring quantum algorithm advantage for space for three use cases. So the first case is a complex problem non-tractable in human time with supercomputer. That means new operational capacities on services, or existing problem, faster resolution than with traditional computer, like electromagnetic simulation, for instance. And so it drives performance improvement by augmenting engineering. And the last advantage is the energy advantage to reduce the CO2 footprint of our application on energy frugality. So in Thales, we have defined two pillars for quantum algorithm for space and to develop at scale these algorithms. So on the left, you have offline engineering, where you could find design optimization of electromagnetic antenna on antenna modes, performance assessment of complex system, massive testing for IVVQ, and electromagnetic simulation. And we are driven by constraint on performances, integrity, and accuracy. On the right is online operation, so massive IMINT and ELINT processing, system reconfiguration, anomaly detection, resource allocation, and mission planning. But as we are addressing a critical industrial system or military critical system, we are also very interested by quantum code analysis and verification. And we are also a coordinator of the French initiative BAC for application-oriented benchmark of quantum computing. So we have launched different actions. So we are structuring our team for preparing application of quantum algorithms, so to master the use of quantum computers on software libraries, to accelerate the benchmark of quantum algorithms, and to develop engineering. So we have created a dedicated team based at Thales Research and Technology and at International Quantum Hub. We have consolidated more than 20 benchmarks, and we have access to quantum French facilities like CEA, TGCC. And we have different cooperation integrating Terra Quantum collaboration. So we are also collaborating with a French startup, Pascal, Candela, and Alice and Bob. So we use this ecosystem also to benchmark and to test the different technology, because in French we have the chance to have the startup covering superconducting, trapped neutral atom, photonic, and spin qubit. We have also tested anomaly detection on series of satellite images. This is a collaboration with Fraunhofer Institute, where has been developed an hybrid algorithm running jointly on quantum annealer for extraction of points, on mapping on NISC using Fraunhofer facilities and access to IBM quantum computer and D-Wave quantum computer. And recently, we have been selected by European Space Agency for a project which is called Quantum Computing for Earth Observation, which is led by Rulich in Germany, but with IQM in Finland, ENFN in Italy, and Thales Alenia Space in France and in Italy. So now I give the floor to my colleague from Terra Quantum to describing the collaboration.
Thank you, Frédéric. Amazing. So I'll tell you a little bit about Terra Quantum and what we do, and then go really deep into the problem and the collaboration that we had with Thales. So firstly, Terra Quantum is a quantum as a service company. We work across algorithms, compute, and security. We've raised one of the largest fundraising rounds with more than 100 million in funding. We're well backed by Lakestar and InvestCorp, which is one of the first few PE firms to invest in quantum, which just showcases the maturity of our offering. We have over 200 people all across Europe and North America, solely focused across the entire quantum information science spectrum. A core aspect of our approach is to hybridize, given the limitations that we have in the NISC era. So what we do very effectively is build hybrid quantum software and run that on simulators and test that on native QPUs. And we see this aspect of hybridizing the donut or completing the donut being essential not only today to drive performance, but also in the future. Very specifically, we have a suite of algorithmic products across optimization, machine learning, and simulation, where we use 4 problems, all the way from black box optimization to tensor networks in simulation. In this specific case with Thales, we used a lot of our machine learning and optimization products to drive the results. And just to give you a bit of a flavor of how we work, so we do the whole end-to-end. We focus very much on the end application. We bring in the domain expertise as well in our team. We're very much looking to drive enhanced performance on the application layer, build the hybrid quantum algorithm, run that in a hardware-agnostic fashion, either on the QMware hybrid quantum cloud, which is a joint venture we have with Terra Quantum, which combines the best of the classical world from supercomputers and HPCs, CPUs, GPUs, but also brings into the picture QPUs and quantum simulators. QMware is very unique, as in its in-memory compute system has a very large RAM, which enables it to integrate with QPUs on a physical level rather than just API or SDK access. And this enables us to solve really complex problems and having these schedulers run workloads across both the classical and the quantum system. Just some examples of work. We'll go into the Thales work specifically, but we also work with Volkswagen Group on quality control inspection and workflow scheduling. We work with Uniper on options pricing, LNG logistics, shipping, as well as kind of prediction in power plants. And lastly, we recently released a lot of work we did with Evonik, which is a specialty chemicals company in fluid mixing simulations and shape optimization, really kind of looking at how we could use tensor networks and physics-informed neural networks to drive a performance for these complex shapes that they're looking to optimize. So now getting into the heart of the problem. So this is one of the most fascinating problems I think we've worked on. It's mission critical as well in terms of its significance. For some color, like the search space of the problem is humongous. For some context, ESA estimates that the number of observable stars in the universe is about 10 raised to 22. So 10 raised to 1,700 is kind of the search space that we have in a 2-day period for optimizing the satellites in the mission plan. These satellites get about 2,000 to 5,000 requests regularly, okay, every 8 hours that they need to sort through. And there's also a time constraint on this. So we want to do this within kind of 10 minutes. And so, considering this large search space and an existing algorithm, which was a heuristic-based greedy algorithm, we look to kind of tackle this problem. So if you just bring it to life a little bit more, so these satellites, they go around the world in these specific orbits, okay, where they have to take pictures when they go on these orbits of the Earth at particular points. Now, what does that actually mean, right? So when the satellite is going on this orbit, it has certain periods in that orbit where it can take a picture. Every picture has a certain value associated with it, and if it can take pictures of higher value, the satellite is more operationally utilized and it makes more money, in the simplest words possible. Some parts of those trajectories are harder to take pictures at, like for example at the equator, it's really hard to do that, versus more at the poles where it's easier to do it. And these orbits, the satellite completes about 15 orbits a day, so it's not a problem that is a one-off problem. We're solving this every 8 hours for the next kind of 2 days through the satellite control center. If you look at the specifics, like here, we're really trying to improve quality of the solution because most of these satellites, optical imaging satellites for Earth observation, are only 80% utilized. This is something that Thales Alien Space really wanted to improve, as well as the kind of computational time associated with it. So there's a bottleneck of solving this problem within 10 minutes that we're trying to look at. And what we always do is try to bring the value aspect into consideration. So every request had a different amount of value, with the most valuable request being circa 10,000 euros per request if it was facilitated. So what that means is that if we take a picture which is worth 10,000 euros, that satellite would satisfy and do some good when it's on these orbits. The picture on the right-hand side gives you a little bit of a visual kind of image of how this looks. So the satellite goes within this trajectory, and then it tries to take a picture of a certain part of the Earth. Where it takes this picture really matters, because it will influence the quality of that picture, and in turn also the price or the value that it gets from that request. There's some other things that made this problem incredibly complex, like the constraints associated with them. I won't get too technical in this, but there's something called as relaying maneuvers that the satellite needs to go through between these acquisitions before, when it takes these pictures, and then also maneuvers that it needs to be to take place when it is having an acquisition. So these are called guidance maneuvers. There's other aspects as well that we look to address in production, like solar charging, because these satellites have these solar panels on them that they can use, and energy management is very important, as well as kind of attitude maneuvers to the Earth. So when there's certain eclipses, we need to have different kinds of behaviors that we need to facilitate in the problem. So feasibility is something that we look to facilitate within giving the solutions, and we see that not only with Thales in this use case, but across the board, feasibility being the aspect that makes things really, really complex. So what is complexity in this case, right? So complexity here is really scaling with two things. One is the number of satellites and the number of requests, okay? In the proof of concept that we did, we looked at roughly 2,000 requests and 2 satellites, and that's where we're today. However, as we move to production, we're looking to increase complexity, look at more and more satellites, up to 20 satellites and 50,000 requests. However, even today, with just 2 satellites, a lot of defense departments at countries have just 2 satellites in their constellation, and they could use the solution that we have even in the current level of complexity. So just to get into the actual problem that the solution that we had, Thales had a greedy algorithm. We combined our approaches in machine learning and optimization to give a mission plan, and then we compared that mission plan to see who had a better mission plan associated with it. Just to visualize it a little bit more in terms of the formulation, so if you imagine these different kind of requests that you have, every request has a specific time window, which are the black bars that you see, and within those time windows, we need to kind of find the right slot for where we actually take that picture. So, if we go and look at it further, the green slots are where, the satellite would take that guidance maneuver, do a guidance maneuver, and take a picture. But the added level of complexity is with the other relaying maneuvers between the satellites. Now, this brings in a factor called chainability. So a decision that we make at request 1 impacts request 10, for instance. So, there's a lot of dependencies and highly coupled aspects or states in the problem that we had to kind of consider. Now getting to the solution and being very specific, so what we try to do is combine the best of the classical and the quantum world. So we had 2 approaches, machine learning and optimization. In machine learning, we looked to use reinforcement learning, which was we use AlphaZero from DeepMind, and also something called as PPO, or proximal policy optimization. We had hybrid quantum versions of that, and I'll explain what that exactly means. And on the optimization side, we had a MILP related problem that we could solve using existing solvers, but also Cubo version that we could run on the D-Wave vanilla. So when we talk about hybrid, we truly look to hybridize on both the software level and the hardware level. And the hardware specifically is through QMware, but on the software level, we are always looking to how could we potentially combine, add quantum elements in, use classical that is state of the art today and improve it, or use quantum to improve the classical, vice versa. So what does this actually look like, right? So getting into the specifics of the 2 approaches. So in terms of reinforcement learning, we used a PPO, which you see the kind of the classical version on the left-hand side. It's an iterative improvement machine learning method, which is very commonly used for these kind of problems. And on the right-hand side, you see an example of one specific neural architecture. of the hybridized version of it, where you can see the quantum circuit at the end in this instance of the algorithm. And what we observe is that as we change the architecture of this quantum layer, the performance also changes, as well as the position of it, whether it's at the start or actually at the finish. If you look at the other side of things, we've thought about hybridizing alpha 0 as well, and this is incredibly powerful. I don't think anybody else has ever done this before, so this is a novel in terms of hybridizing a very performant existing reinforcement learning approach like alpha 0. And here what we're trying to do is, use a hybrid quantum neural network for the guidance maneuvers when conducting the tree search. So when the tree search occurs, it has a classical neural network that does it today, and we have a hybrid quantum neural network that does the same thing to enhance the performance of that alpha 0. So just to give you some more intuition on like performance, right? So we've written a paper on this, which is already on arXiv and also submitted to an Earth observation journal, which should be public very soon. But here you can see the performance of hybrid PPO in terms of its outperformance with classical, which is the existing method that Thales currently had. You can see very clearly, like, you get much higher reward with fewer steps. And this is something that we're trying to exploit more and more. We see generally with hybrid quantum machine learning is that you get greater prediction accuracy at lower epochs or with lower data. And though this is not generalizable, it's very specific on the data, very specific on the instance that we're looking at. Just to give you some color, we also had the optimization side of things, which had integer optimization and the QUBO. I won't get into the specifics here, but what we tried to do is use a combination of classical solvers like FICO Express and such, together with QM machine and the D-Wave machine to see how we had performance. And we have the specifics of, what is the quantum contribution specifically or quantitatively in comparison to the classical contribution. And I think that's something that's very important to always have, is clarity on what is actually quantum and what is actually classical across both software and hardware, and to quantitatively measure that in terms of its contribution to the performance. And that's something that we continue to do as we see increase in complexity of the problem. Just getting to a summary of the results, this is also in the paper, so you can read it there, but overall we had an improvement of 1 to 1.5% in optimality with the machine learning approach that we had in comparison to the existing Thales benchmark of 97.5%. This is powerful in many ways, and also a great result, which I think we're very, very happy about. This is the paper which you can read online and ask us lots of questions on if you fancy. Just to step back a little bit, right? So the way we're thinking about this is that satellite mission planning is one application amongst many applications in space. And we see, the directional arrows of progress really heading towards being, space being more privatized, the number of satellites in orbit increasing, the burden to increase the operational utility of the satellites also increasing. And the market for this is roughly about $6 billion today. And so there's lots of opportunities to kind of use the solution that we have in a commercial sense as well. And just to finish off, lastly, I think this was a very nice collaboration that we had with Thales. The lessons that we had was that it worked really well because we had a combination of deep domain expertise and practicality in terms of comparing it to existing approaches. And that's something that we will continue to do at Terra Quantum and with our further collaboration with Thales. Thank you very much.
Any questions?
Thank you, both of you. Very nice presentation. I'm just wondering, because PPO is basically your cornerstone of this scheduling network, right? I just want to know how scalable it is in a quantum version of that.
Yeah, that's a very good question. So we have not evaluated scalability with increase in complexity yet of the quantum version of it. All we have is initial results on the current level of complexity. But generally what we see is that as the level of complexity increases, specifically for this problem, the classical approach falls short, very specifically with regards to finding a good time to solution for the problem. So hopefully, you know, as we kind of move to the next phase of collaboration, we'll have more color on how that scales, the quantum aspects, not only for PPO, but also the other approaches. Yeah.
Maybe if you can ask one more, if there is no.
Yeah.
I mean, looks like it's a very agnostic framework, right? I mean,
Yeah.
it's basically scheduling, right? So how do you think it's scalable to other domain? Like, do we need to change anything with this one, or is any specific for the satellite communication?
It's highly specific for the satellite communication. Yeah, it's very, very specific because the beauty of it as well is that we can only see the performance because it's so application specific, where we try to build the formulation around the problem and then see how you can use quantum in that instance. In terms of reusability or like scalability in a wider context, what we always try to do is enhance or keep building on our product portfolio, so that you could use a standardized Terra Quantum product and then add a level of customization to it for your specific problem. However, that customization layer is still complicated. It still requires a lot of work to drive the performance.
Yeah. Thanks.
Yeah.